Hello, yeah, some more electric fields questions. Here we've got an arrangement used to accelerate electrons. So we've got a hot filament hooked up to the negative terminal with this 1500 volt supply. Electrons are pinging off of that through this gap in an anode. Draw an arrow to show the direction of the electric field at point A. So the direction of the electric field is what would happen if we put a positive charge in there. What way would a positive charge move if we put it at point A? Well, it's going to move towards the hot filament because it's negative. So it's going to be an arrow off to the left there. And of course, the positive charge is going to move in the opposite direction to the negative electrodes. So, right, that's fine. Potential difference between the filament and the anode is 1500 volts. Yeah, we know that. Speed of an electron at the filament is negligible. Determine the kinetic energy in electron volts of an electron at the anode. Right, so an electron volt is just the amount of energy that you get if you move an electron through 1 volt. Now we're moving electrons through 1500 volts. So that is just going to be 1500 electron volts. That's the whole point of electron volts. Calculate the speed v of an electron at the anode. Right, okay, so now we're doing our half mv squared is equal to this. So we need to change from electron volts into joules. So we're going to do 1500 electron volts multiplied by the charge on the electron is, this is our joules per coulomb multiplied by coulombs is giving us our joules. Now that's equal to half mv squared. So if we multiply that by 2 and divide it by the mass on the electron, then that's going to give us v squared. And then we just need to square root it all, is going to be giving us our v. You'll be doing this so many times in these sort of questions. So that is giving us that v is then, let's write it properly down here, 2.295 times 10 to the 7, which is 2.3 times 10 to the 7 meters per second to two significant figures. Right, so nice little warm up there. Assume there's more to it. Here we go. Right, electrons from the arrangement shown in figure 3.1 enter a region of space occupied by uniform electric and magnetic fields. Okay. Electric field strength is E, which is going down. Magnetic flux density is B, which is perpendicular to E into the plane of the paper. Okay. B is increased till all of the electrons pass through this slit. Okay, so we're doing some kind of mass spec type approach on this velocity selector. Path of the electrons is now horizontal. Derive an expression for V in terms of E and B. So yeah, this is your velocity selector. So we've got for our magnetic field, we've got that the force is equal to B, well, these are electrons, so let's go EV. Then for the, what am I saying? The electric field, we've got the E is F over Q. So that means that our F is going to be E times Q, which is E times charge on an electron, because we're dealing with electrons here. And these things have got to be the same. So we're saying that BEV is equal to E times E. Now, there's a lot of E's here. So we got the capital E and the little e for the charge on the electron. We can cancel those and say that our V is E over B. So that's velocity selectors for you. The magnetic flux density is increased further. Electric field strength is unchanged. Describe and explain what happens to the path of the electrons. Right, so we're increasing magnetic flux density. Right, so what's happening here? Let's think about how we've got, when it's going through the gap, when it's going horizontally, then we can see the electric field is pointing downwards. So the force from the electric field on an electron will be upwards. So we've got an upwards force from the electric field. So we must have a downwards force from the magnetic field. Now we're increasing the magnetic force. So this is increasing. So it's going to bend downwards. So we need to describe and explain. So we're going to want to go through those steps then. So we can say when horizontal, we have FE upwards, but don't write an arrow, actually write upwards, and FB downwards, where FE equals FB. As FB is increased, I'm going to actually write increased because I've used the arrows for pointing upwards and down and downwards. Resultant force is downwards. Therefore, the electron will move downwards, moves down. So yeah, but you can see how that balance is coming about here when you're getting this velocity selector going on, that we've got these two opposing forces. So yeah, just make sure you've got it clear in your mind with these electric field lines. Electrons are going to be experiencing a force in the opposite direction to the electric field lines. Right, that was a nice question. I like that one. What we got now then? So, this looks like we're going to be drawing in field lines. We've had something like this before, but I think this is a slightly different question. The potential difference, 60 volts, yeah, 5 millimeters. Draw the electric field pattern between the plates. So we want to have evenly spaced vertical lines. They said between the plates. I mean, you could draw some of the slightly bulgy ones on the outside. You want to try and get your 90 degrees is on all of these, and we're drawing in the field lines from positive to negative. So we're drawing them all in, going in that direction. So from high to low. Put in at least 4 or 5 lines. Otherwise, they're not going to be that keen. Right, calculate the electric field strength between the plates. So E is V over D, which is 60 divided by 5 times 10 to the minus 3. So that's 12 times 10 to the 3, so 1.2 times 10 to the 4. So you can say volts per meter, newtons per coulomb, whatever you want. I mean, different ways of describing the electric field strength. So that is good. I've got a feeling we're going to need to use that 1.4 times 10 to the 4 on the next bit. So I'm going to make a note of that. 1.2, I mean, times 10 to the 4. That's our electric field strength. Volts per meter, newtons per coulomb, whatever we want. Right, let's push on with a lot of stuff here. Positive ions are accelerated from rest in the horizontal direction through a potential difference of 400 volts. Right, okay, yeah, so this is the usual setup. We've accelerated some ions out of here through this 400 volt potential difference. Then we direct them between the parallel plates where we've got the electric field, and then they're going to bend off. We can see that it's positive ions because remember our electric field, the arrows, they're all going from high to low on the voltage. So that's telling us the direction that the positive ions are going to be moving in. So they're bending down in this case. If it had been electrons, they would have been bending upwards. They've given us mass and charge of the ions. Show that the horizontal velocity of an ion after the acceleration by the 400 volts is that. Okay, right, we're back on the kinetic energy thing again. Right, so our energy of accelerating through the potential difference is our joules per coulomb multiplied by coulombs. This is our charge. So 400 multiplied by 3.2 times 10 to the minus 19. Just make sure you get the right voltage. Of course, you're being accelerated, across this 0 to 400 volts, not the 0 to 60. So that's our energy. That is equal to a half times the mass, which is 6.6 times 10 to the minus 27. It's got feelings of an alpha particle about it. And because, we've got 2 times electric charge and, anyway, doesn't really matter. Multiplied by V squared. So we just need to do the usual rearranging. So, and then square root everything. So I'm not going to write out the formula because I think I would push the I'm not going to rearrange it all on here. I'll run out of space. I'll just type it straight into the calculator. 1.969 times 10 to the 5, which is 2.0 times 10 to the 5 meters per second to two significant figures. So that was that bit. Right, the ions enter at right angles to the uniform electric field between the plates. Calculate the vertical acceleration of an ion due to this electric field. Again, we've done this loads of times. We're using our two different ways of describing electric field strength. So we've got our F over Q, which is V over D, and equals F over Q is, well, our F equals MA. We're sticking in there. So, and we've also got, yeah, F equals MA, and we need to work out the vertical acceleration. So, therefore, we got that A is equal to Q times V divided by M times D. Again, we're just straight to the calculator with all of this. Going to be quite a lot of typing in. This is going to be a really high value, like 10 to the 10 or more even. What is it? 5.8181818. So 82 times 10 to the 11 meters per second squared. So 5.8 times 10 to the 11. Make that look clearer as 11 meters per second squared. The length of each of the charge plates is 16 millimeters. Show that the ion takes not very long to travel through the plates. Right, so that time is going to be our distance divided by the velocity that we worked out up here. So we've got the, where am I? The distance, so 1.6 times 10 to the minus 3 divided by 1.969 times 10 to the 5. So that's going to be pretty close to that, and lo and behold, it is 8.0. Well, it's not 8.0 actually. It says about. I mean, mine's come out at actually 8.126 times 10 to the minus 8 seconds. But there's so much rounding going on in all these different steps. It depends whether you're using two significant figures or what. You know, if you put a 2 into here, you're going to get 8, aren't you? This is going to be a little bit more because I've gone back to the 1.969. They won't care about that on the mark scheme. So 8.1 times 10 to the minus 8 seconds. Calculate the vertical deflection of an ion as it travels through the plates. Right, again, this is a classic. So our change in velocity is the accumulation of the acceleration. So we worked out the acceleration, we've got the time, so we're just multiplying these two things together, the 5.82, the 8.13. Multiply all that together, that gives us our change in velocity. But to save a bit of space, let's go on to the next bit. So our change in displacement is the average velocity multiplied by the time. So that is half of the change in velocity multiplied by the time, multiplied by the 8.13 times 10 to the minus 8. And that's our change in velocity there, which is, yeah, as I say, it's the 5.82 times 10 to the 11 multiplied by 8.13 times 10 to the minus 8. Essentially, this is S equals UT plus a half AT squared, but I don't like using SUVAT because I just think it's too opaque. This is really simple in terms of describing our, you know, all of our kinematics. So, you know, why not go to a better conceptual understanding of it rather than using SUVAT all the time? So anyway, I'm plugging all of this into the calculator, getting 1.9 times 10 to the minus 3 meters, which is fine. We've got a 5 millimeter gap here. It's not going to be going in right on one edge. You know, you can see here, if it comes in even slightly towards that 60 volt plate, moving down 1.9 millimeters is fine. It still keeps us between the plates. Right. What bit was that? I've lost where I am on the questions. Right, we've just done that. Right, part C. Uniform magnetic field is applied to the region between the plates. The magnetic field is perpendicular to both the path of the ions and the electric field. Calculate the magnitude of the magnetic flux density needed to make the ions travel horizontally through the plates. Right, so how are we going to get our velocity selector working on all of this? So we need E times Q has got to be equal to B times Q times V. You know, we've just done this. So we can cancel the Q's. We can say then that we need B to be equal to our electric field strength. All right, so we did eventually use this. 1.2 times 10 to the 4 divided by the velocity, the horizontal velocity. Where was that? 2 times 10 to the 5. So 2.0 times 10 to the 5. So that is 0.06 magnetic field, so Tesla. Ions of the same charge but greater mass are accelerated by the potential difference of 400 volts described in B. Right, okay. So we've got heavier stuff. Describe and explain the effect on the deflection of the ions after they've traveled between the plates using the same electric and magnetic fields. Right, let's take this onto a new screen just to have enough space to go through all of this. So we had our parallel plates. The electric field is going down between these plates. So when we've got a positive ion, which is traveling between the plates, then we've got competing forces on here. This is a positive ion, so we're going to have a downwards force due to the electric field, and then we were balancing that with an upwards force from the magnetic field. So we've got those two forces there which are equal. And then we've got a number of equations that we were using. So we were talking about the kinetic energy when it was accelerated through this 400 volt potential difference. So we've got that kinetic energy, half mv squared. We had the force from the electric field, which is E times Q, and we got the force from the magnetic field, which is BQV. So we want to use these equations and just describe what's happening in each one when we change the mass. So we'll go through each one in turn, right? So we're going to say, right, so if mass increased, then we can say kinetic energy unchanged, because we're accelerating through the same potential difference. So we're getting the same amount of energy. So therefore, let's put and in there, therefore V decreased. Right, so we've got that for a start. We know that the velocity has dropped. Then we can move on to this one and say, right, FE is unchanged because E and Q are unchanged. Then we can look at FB. We can say FB decreases, or has decreased, because we've got that B and Q unchanged and V decreased. So that means we've got FE is unchanged, our downwards force. Our upwards force has decreased. So therefore we can say resultant force is downwards. Therefore the ion, the positive ion, moves downwards. So yeah, you want to get that chain in. So, and it's built around all of these different equations that we've been using, and you just want to say what has changed and what hasn't. And they haven't changed very many things. They've kept, that's the same, that's changed. So they've changed one thing there. What's the effect of it? V has decreased. Then on this, they've changed nothing there, and then we've only had one thing changed there with the V. So yeah, just set it out in that nice logical order, just talking about each one of the equations. If you put the equations down one at a time, it gives you some structure of what to say. You don't necessarily need to write all of these out again, but there's not a lot you have to put on all of this in order to describe it all. So yeah, I think those sort of questions with the parallel plates are possibly the most difficult ones in the electric field questions normally, because you've got description, you've got calculation, it's all quite involved. They're quite long questions, but they come up a lot. So just practice them quite a few times just to make sure that you're slick on them.